This lesson is one of my favorites because we talk about money, specifically how it relates to growing interest. So we have talked about rather that things can grow exponentially. Like a virus spreads exponentially, or population grows exponentially, things like that. But what's great about this is money can also grow exponentially. When you invest it and it's collecting interest, it will take a while to start really moving, but it does take off and it does grow exponentially, but it takes a lot of time. It doesn't grow quickly at the beginning. And this is because of compound interest, because really what happens is they add, once the bank or whatever adds in your interest amount, it then starts gaining more interest because the old interest is already added on. So now that's your money, and you start getting more and more compounded interest. So it will have a look like this, but it does take some time. I like this quote. I don't know if it's actually from Albert Einstein, but it, according to the internet, it is. So it's the most powerful force on the universe is compound interest. I doubt that's actually true, but maybe. So, compound interest is when interest begins to make interest. We have a couple of pieces to this and an equation also. P is the principal, which is your starting amount. A is what is called the amount. It's the ending amount. R is the variable we'll use for interest rate. N stands for how many times is compounded in a year. So different places, different banks, different accounts will compound differently. I have a savings account that compounds monthly. At the end of every month, they add on me the interest that has been gained, and that gets added into my account. And then the next month, that all creates or collects more interest. The downside to all of this is banks look at this, and like when you have a car loan, it's compounded daily, and that works against you. So if they add on the interest that you owe to the bank every day, but then say you had a savings account, they would only add on the interest once a month, or sometimes even once a quarter. So that's what banks do, because they are a business. They are making money. That's what they are set out to do. So the compound interest formula is A equals P, parentheses, 1 plus R over N, and then the exponent is NT. So exponents, the bigger the exponent, the bigger the return, the bigger the growth will be. So the two things that work with that are N, how many times it's compounded, so that can help you out, and then T, which is time, the amount of time that is in there. And also, it doesn't have as big of an impact because it's also in the denominator here, which means it's going to make the rate that's done each day, or however often, less, because it's an annual interest rate. So T is the most powerful factor in this entire equation. So related to that, we talked about N is how many times compounded in a year. So here's some vocab you need. Annually means once a year. Semi-annually means twice. Quarterly is 4 times. Bi-monthly, every other month, would be 6 times. Monthly, obviously 12. Daily would be 365. If it's a leap year, it would actually be 366, but on our word problems, we'll assume it's not a leap year. If it says daily, we'll just do 365. I pulled up this website from DaveRamsey.com. He's got this investment calculator. He's a pretty famous, well-known financial advisor, I guess. He has his own radio shows and stuff like that, and books and things that he writes about. So I went ahead and just threw in some numbers here just to show you how time does actually impact this. I entered age 18 just because that is really about the time that you can start. If you're under 18, it's hard to get these things going. You can with the parent signing off on it, but you can start a retirement account around that time. If you just threw in $10,000, no 18-year-old's probably going to have $10,000 to start out, but just to kind of show you what that would look like without giving any more money. And we'll talk about a more realistic example here for you guys in a minute. And then for any 30-year period, historically, it's always gained about 12%. We're going to go a little bit more modest. I typed in 10% there. But just to show you how much time can impact this from age 18 to 67, that $10,000 would actually become over $1 million. $1,315,000. So you're actually, all of that would be growth. All of that would be in addition, well, almost all of it, to the $10,000 that you started out with. Now, if you look at it, it takes a long time to really get going. And then the later years are when it really takes off. That's what the exponential growth part looks like. So if you started it now, even 24 years later, there's not that much. It's only 100,000. 24 years later. But then another 20 years and it really takes off. And then those next couple of years really are growing. So that's just kind of the idea. Now, like I said, let's do some more realistic things for you. And this is a great website just kind of go and play around with. Say you have no money when you turn 18, because that's pretty likely. But you are deciding that you're going to be committed and just put in a little bit of money each month. I don't know, we'll say $100 just to see what that looks like. $100 per month, typically you'd be paid at least twice a month, so that's like $50 a paycheck. It's not that big of a deal, but if you start that when you're 18 and let it go until you're able to retire with that same 10% interest, you actually end up with even more money. The last example we had was $1,300,000. This is $1,500,000. So it's a super easy way to make sure that you're set. It's just small bite-sized pieces, really. Again, you won't really feel like you have anything. It's going to take a really long time. Even 24 years later, you only have $100,000. It doesn't seem like much, but just remember the big picture. I have $1.5 million over that. This would be a 50-year period almost from age 18 to 67. But super easy, super applicable to your life. $50 a paycheck. You could probably do that with even a part-time job if you don't have a lot of bills while you're in college or something like that. You could still do $50 a paycheck often. So hopefully you guys can actually take advantage of that. Now, if you're old like me and you haven't started this yet, it doesn't work out that well. Let's see, I'm almost 37 next month. So we'll go with that. But if I don't have any money right now and I start this, it's not going to work out that well because that's only 30 years, and we looked at the 30-year thing already. It'd be too late for me to start out at that. I'd have to make bigger contributions monthly, or maybe already have something saved, which I did start this before, earlier in my life, so we do have some money. We're about that far along, somewhere around there. And we actually contribute more than that. So having some money and contributing more is still okay. That actually works out pretty well too. So something around there. Those are some realistic numbers for you guys. See if that's saved correctly. Yep. So it doesn't have quite the growth because it's not the amount of time, because I'm already into this plan a little bit. So, but it works out okay. So you can have some real life examples there. It's a great website to kind of play around with. I think it's fun to mess with these numbers and see what it takes. But just remember how easy that would be for you guys to have $1.5 million. It's just like $100 a month, $50 a paycheck. Stay committed, actually do it, and you will make sure that you're set for later years in your life. All right, coming on to some actual examples here. Now, when I go through these, I'll explain as we go on, but first step for every one of these word problems is I write down the word parent. Now that comes from almost all these words. You can see P-A-R-N, T for time. The only thing missing is the E. We're not going to use E yet. It comes about in a little bit. With continuously compounded interest. So we're not going to be using it currently. We'll use it later. Future problems we'll get to. So going through each of these variables, once you write them down, you just have to identify them from the word problem. Makes this pretty straightforward word problems. The annual rate of 7.5%, that's R. That'll be 0.075. Write it as a decimal. When we type it into our equation, we'll need the decimal for it. $2,000 is invested now, so that's your principal. It's compounded annually. Annually means one time per year, so that's N. How many years, that's what we're solving for, T, will it take for your money to double? So a really small math problem to get that number for A. Money to double is you're going from 2,000, double would be 4,000. So now we have our equation. We just need to plug it into the formula, which is A equals P, 1 plus R over N. A equals P, 1 plus R over N to the N times T. And we're just solving for X. So to solve this, that is an exponent where we're solving for our variables, so we need to isolate. I simplified a little bit. Instead of dividing by 1 and multiplying by 1, we don't need those numbers there. And now we're solving for X. So when we solved these the other day, our next step was to do natural log. And then we can move exponents to the front. Our parentheses here, 1 plus 0.075 is just 1.075. And we're solving for X, so that's division. And then X is by itself. So let's get out our calculator. We'll type that in. Natural log of 2 divided by natural log 1.075. And we've got 9.584. Now that was t, so that is time. That's in years. Now if you wanted to break that down into how many months and all that sort of stuff. Now granted, interest is not added on. It's only added on once a year, so the months wouldn't really make sense here. It would happen as soon as you get that interest for the 10th year. It's really how that would work. But if you leave your answer this way, that's okay with me. All right, same sort of problem. Again, start with our word parent. And again, we're not using E yet, so we can get rid of that. 450 is invested, that's our P. 4% interest, that's our R, 0.04. Compounded annually, so N equals 1. How many years will it take for to have $600? So that's not growing by a whole lot. It's not doubling. And we're finding how many years, so we're going to solve that out. So again, we write it into our formula. A equals P 1 plus R over N to the N times T. Let's plug in everything that we know. Now we're going to solve this out. So we're going to divide by 450. It's 1.3. If we want that as a fraction, that's just 4/3. And 1 plus 0.04 over 1 is 1.04 to the x. Now again, trying to get the solving for the exponent means we're going to do natural log. Exponents move to coefficients. Remember this division, if you wanted to, you could write it out. It would actually be more typing, but that's okay. You can write it as a subtraction problem using our properties. Or you can leave it as the fraction. It doesn't matter. And then we're going to divide. So, like I said, it's less typing to leave it as a fraction, so I'm going to do as a fraction, natural log of 4/3. And then we're dividing by natural log 1.04. 7.335. Again, x, that was for our t variable, our time, which is measured in years. So a little bit more than 7 years. Again, we won't get that interest since it's compounded annually. You'll only get it basically for the 8th years when we'll pass that $600, but you can just leave it as the decimal. It's totally fine. Okay, this time we're going to look at what changing how often it's compounded does. I talked about it, I mentioned it earlier, but now we'll actually see it in action. So again, we have our parent. So here, n equals 1. The principal is 1,000. 10% annum, that just means 10% is our rate again, 0.1 or 0.10. how much money is in the account at the end of 1 year. So now we have t equals 1 year. We're finding our final amount. So we're really doing this problem twice. And the second time, n equals 4. Everything else stays the same though. So as we work this out, we have a equals p 1 plus r over n to the n times t. So this, we just have to work out. There's no need for a logarithm or anything like that. This is 1,000 times 1.1 to the first power. So that's 1,000 times 1.1. It's 1,100. That was A, so that's money. $1,100. And our second equation, when n equals 4, same idea, set it up. But this time we have n is 4, and then to the 4 times t. So this changes out our equation. It's going to change our answer also. We have 1 plus 0.1 over 4. So 0.1 over 4. And it was 1 plus that, so it's 1.025. And our exponent is 4. So to the exponent of 4, we do exponents before we multiply. So we did 1.025 to the 4th, and now times 1,000. So it's 1,103 and 81 cents. So that's about how it works out. It's not a huge difference when the number of times it's compounded, but it did work out to be $3.81, which isn't a ton of money, but it is money, and it's free money if you just get to choose how often it's compounded. And that's exactly why the bank does that. Normally they would give you compounded less frequently than they would compound the money that they're going to be getting, so that way they just come out a little bit ahead, especially when they have then thousands of accounts. So $3 per person, and then you have thousands or hundreds of thousands of accounts. That's almost 4 times the hundreds of thousands, so like $400,000 or something, however it would work out, and that's just for simple accounts like that. That's why they make that difference. That's because they do make money that way. All right, same setup. This time we're looking at different compounded times again. One last thing, just real life numbers. 10% in a savings account doesn't happen. Currently, the best you can get is a little bit less than 2%. 1.75% is actually like real life savings account numbers. And but stock markets and things like that over a long period of time typically will get 10% or something around there. Except this year. This year is not good. So it's a negative percent. You're actually losing money in the stock market this year. So Savings account 6%. That's a little bit closer to real life. Like I said, it's really under 2%. And if you just had a regular account, like with Wells Fargo or one of the big banks, it's actually like 0.01% or something like that. So just be mindful of it. Shop around your savings accounts. I actually just switched because the bank I had went from 1% to, it was closer to 2%. They dropped it down to 1, so I switched banks, and now I'm going back to a 1.75% account. So that just makes a difference of, a few dollars over the course of 1 year or something like that, but it's a few free dollars. So, all right, $3,000 deposited in a savings account. So we're going to do the same thing we've been doing, that parent equation. Now for all of these, again, we haven't done anything with E yet, so we can just cross those out as we go. So all of these, we're going to have the $3,000 deposited, so that's our principal. All of them are wanting to know how much money is in the account after 2 years, so we're solving for the final amount. After 2 years, and all of them have the same interest rate of 6%, so 0.06. And then N changes based off of these words here. Annually means N equals 1. Semi-annually means N equals 2. And daily means N equals 365. So we talked about this on the last problems, but now we'll see it again. So now we need to write out our equations. A equals P one plus R over N to the N times T, 1 times 2. And for our second equation, same thing. A equals P one plus R over N to the N times T, so 2 times 2, that's 4 for our exponent. And our last one, A equals P. Whoops, I'm missing a 0 here. 1 plus R over N. N is now 365. And then our exponent is N times T. So 2 times 365. $730. All right, so we need to solve each of these out. Calculator time, start with the parentheses, then exponents, and last multiply. So 1.06, when we do the parentheses, to the second power, and now multiply by 3,000. $3,370 So same process here. We need to start with our parentheses. 1, 0.06 divided by 2, so that would be 0.03. Still type it in, but now we're adding the 1 onto that. There's our parentheses. Now to the 4th power. And now we multiply by the principal of 3,000. It's 3376. And 53 cents. All right, and then our last one, just looking at compounded daily now. So now we again start with our inside. So the fraction, 0.06, divided by 365, plus 1. Now to our exponent, which is 730. And now times the 3,000. $33.82.46. So just comparing those again, the difference between compounded once and twice was a few dollars. And then compounded daily, comparing it back to compounded once, that's $12. So it makes a difference, especially over a longer period of time than just the 2 years. Okay, so now we're going to look at compounded continuously, which actually I've never seen done with money except for in a math classroom, so kind of weird, but it's easy. And compounding continuously does happen with things like bacteria and populations and things like that. So that's where it really happens, but we'll start with money just because money is easy to work with. So we start the same way. The principal is 100. When will the balance reach 150? So that's our final amount. Our interest rate is 5%, so 0.05. And then when will it reach? That's time, so that's going to be our x. Now, here's the thing that we're looking for to know that we're doing this is on our previous problems, it said compounded annually, monthly, daily, something like that. This one says compounded continuously. So when it says continuously, instead of crossing out E, we cross out N. That's the only difference. And by not crossing out our E, that tells us that we're using this other formula, which we had written on the last slide, but here it is. There it is on the previous slide. That's the only difference. We use a different formula because it's compounded continuously. Instead of having an N, we have an E. So plug in what we know, 150, and then R times T, so 0.05x. So again, divide. That's 1.5 equals e to the 0.05x. And we'll follow the same process we do anytime we have a variable in the exponent. It'll be natural log both sides. Move that exponent to the front. And then we had property we talked about in previous lesson about natural log of e. It's just 1. It kind of looks like the word 1 even, O-N-E almost, but it's L-N-E. It's 1, it's gone. When you multiply by 1, it doesn't matter. If you type that into your calculator, you would see it as well. Natural log of e is 1. So, even if you forgot it, you could type it into your calculator if you have your calculator available. But, so now we're finishing this off. We just need to solve for x, so we divide by 0.05. So that's natural log of 1.5 divided by 0.05. 8.11. And again, x, that was in place of our variable t, so that's years. All right, we'll take a look at another one. Same idea. Every time you have one of these money problems with interest, just write down the word parent, fill in your variables. How long will it take to double 8,500? So we've done this before. That means you start with 8,500, and it's going to double. So double 8,500 would be 17,000. Use your calculator if you need to. 4.5% is 0.045. Compounded continuously means we're using e crossing out n. And then how long, that's t, that's what we're solving for. So by crossing out n, we left e, that tells us we use a equals PE RT. So that's the 1,700 equals 8,500, or 17,000 equals 8,500. E to the R times t is x. So, solving this out, now, since we're dividing here, and we got that number by doing double, we know that that answer is going to be 2. Again, if you had to use your calculator, no big deal, but save yourself some time if you remember. Just think it through. And now, finish it off. We're trying to solve for our exponents, so our step's going to be natural log both sides. Exponents to the front, and natural log of e is going to cancel, so that's natural log of 2 equals 0.045x times natural log of e, which is 1, so that's gone. You don't have to write it even. Or you can, and then cross it out, or whatever you want to do with it. So divide by 0.045. So it's 15.4. And again, that was for t, so that's years. So there's a little bit of a shortcut here. If you remember, this doubling formula is just natural log of 2 for double. All the time it's going to be double is natural log of 2 equals r times t. You can use that formula for doubling. Anytime it says double, you can do it that way. Natural log of 2 equals RT. We'll use this again in our next lesson. We talk about half-life also. Instead of double, it'll be half. But these are some real-life formulas You can use in banking. They look at this doubling time is actually a big formula that they use. All right, so that is it. Long lesson today, long video. Hopefully you found it useful. Hopefully you liked it. Go ahead and complete your assignment that's listed there, and you can like and subscribe and do all that stuff that YouTubers say, and leave your comments or post in our class comment section, and see you next time.